Hello, it's Mr. Doro. Today we're going to be talking about polarity of molecules, and you're going to be able to determine whether a molecule is polar or nonpolar just from its structure. Well, we've talked about polar bonds versus nonpolar bonds before, and a polar bond and a polar molecule are related to each other, but they are not the same thing. Polar bond, I've got a picture of a polar bond right here, and this is how you demonstrate that a bond is polar. The arrow always points towards the negative end, the more electronegative end, and the little plus right here is the more positive end. This means a partial positive charge and a partial negative charge. Now this whole thing together makes up a polar molecule because that is a molecule, HF, and it's polar because it has a positive end and a negative end. The picture on the bottom is a polar molecule also. This is a polar molecule because it has a overall positive end and a negative end. This end's more negative on this side. This end is more positive. Now polar molecules have to be made up of polar bonds, and the polar bond in here would be going this way because oxygen is more electronegative, and this way. And overall, these don't cancel each other out, so you have a more negative end on this side and a more positive end on this side. That's what makes a polar molecule. There are 3 steps that you have to do to determine whether a molecule is polar or nonpolar. First step, we know how to do this. Draw the electron dot structure. That's something that we've been practicing over and over again. Also, we know how to determine the molecular geometry from the VSEPR method. And then we need to compare something new called similar regions. So this is really the only part we need to work on today because we should have that other stuff down already. So you need to make a list of these similar regions. The similar regions, I've listed 3 shapes right here. The first shape is linear, and so the similar regions that we're going to be looking at are the ends of the line, each end of the line. Then when there's trigonal planar. Trigonal planar is, remember, a triangle, and the central atom is on the same plane, and so we're just looking at the corners of the triangle. Tetrahedral is a 4-faced figure, and so we're looking at the corners of the tetrahedron, the top and the 3 sides. Make sure you have a list of those similar regions because we're going to need them in just a minute. So here's what the similar regions tell you. If all the similar regions have the same element in them, if the ends on the linear, or the corners of the triangle on the trigonal planar, or the corners of the tetrahedron on the tetrahedral, if they all have the same element in them on those similar regions, then this is nonpolar. It would be a nonpolar molecule. But if they don't have the same element on them, if they have a mixture of elements, and they're not all the same in each of those similar regions, then it is going to be polar. Now each of these assume that we're dealing with our basic shapes that we know about on smaller molecules. I'll talk about some larger molecules in just a minute too. But here's a key point also. If you see bent or trigonal pyramidal, if they end up being bent or trigonal pyramidal, they're always going to be polar. And the reason they're always going to be polar is because they have those lone pairs or those unshared pairs of electrons. Those unshared pairs of electrons make it different around in their electron domains, and so that would make them polar every time. Now for larger molecules, we got to think about something called symmetry. Now symmetry of molecules is very in depth, and we're just barely going to scratch the surface. But what I call symmetry is if you can cut it in half any way that you cut it and it would have a mirror image, then we're going to call it symmetrical, and we're going to call it nonpolar. So if it's symmetrical, it's going to be nonpolar. If you look at each one of these here, this first one over on this side is the benzene molecule, and really these double bonds that are in here, they alternate, but they really alternate back and forth between all of these, so it's kind of, it could be here and here and here. So if you cut this in any angle in half, then you're going to have the same atoms on each side, and so that would be symmetrical, and we would call that one nonpolar because it is symmetrical. And if it's symmetrical, that means nonpolar, and that we'd say the reason is because of symmetry or symmetrical. Same thing with this one. If you cut the other one in half, this is ethene, and so if we cut it in half this way, like this, we would have a mirror image. We cut it in half that way, we'd have a mirror image, and so this one also would be nonpolar. Not all large molecules are nonpolar, but these two happen to be because they were symmetrical. Now if this had a bromine in this place right here, if that was a bromine, then it would not be symmetrical, and then it would be polar. But it doesn't have a bromine, so we're going to get rid of that. Okay, these are some practice problems that we're going to do together, but this is the way that you're going to have to do the problems that are on the next slide. And so if we look at this first one right here, this first one is linear, and it is Cl2. So for linear, we're looking at each end, and if each end is the same element, then we are going to have a nonpolar, and the reason that we're going to put is similar regions. And the next one is also going to be linear, but this one has two different elements on each end. So since it has different elements, those are not similar regions, and that is going to be polar. Polar because of not similar regions. I'm just going to put R for the sake of time. And then this next one, we have to realize that this one ends, that Cl, that part of it is there. This has got two bonding and one non-bonding around the central atom, which is going to be bent. And so this one is bent, is always going to be polar because of that dot dot that's right there. And so since this is polar, this is because it's bent, and bent is always polar. And this last one is tetrahedral. So for tetrahedral, we look at the four corners of the tetrahedron. That's the outsides right there. And we see if they have all the same element, and they do. So this one is going to be nonpolar also because of similar regions. And so we're going to write our reason why each time. Okay, so this is it then. These are 6 problems for you to do. You just need to tell me whether these are polar or nonpolar. I've already got the diagrams done for you, so you should be able to do that. I know that this last one down here looks like it might not be a full octet around there, but that actually is stable with only 6, so don't worry about it on letter C. And for each one of these then, you need to say polar or nonpolar, and then tell me the reason why, like we did on the last screen. Okay, have a good day. Bye-bye.